Here's the instruction decoder. Right now we can handle two commands, one for add and one for move. 101 is add, 110 is move. And we have the adder as well. So 1 plus 0 is 1, 1 plus 1 is 2. Let's say 2 plus 1 is 3, 2 plus 2 is 4, and 4 plus 1 is 5, right? 101 is 5 in binary. So this works well. And now what I want to do is have the actual decoder of the add command trigger the add operation to happen. Right now, all of the operands are 0, so we're seen as 0. But it's a little deceptive because this add operation is always going on. And as soon as we provide an operand greater than 0, then we see that it's actually adding. So what I'm going to do is remove all the buttons, and I'm going to jump these to essentially set the value of these registers if we want to treat them as registers. So we're basically hard coding now, or hard setting this button, which is the first byte, we could say, it's only 2-bit, but so the first operand to 10, which is 2. I'll turn on the second one as well to 2, so we should get 4 here. Wait, that's on this side. So we should get 4, because 2 plus 2, 10 is 2, and 10 is 2, 2 plus 2 is 4, so 100 is 4. And then I'll turn on one of these just to make it 5. So we got a lot of lights, so I'll turn on this 1. So now we can see we have 1 plus 10 is equal to 5, right? 1 is 3 plus 10, which is 2, equals 5. So we see that our add is always on right now. And we really only want it to be on when we receive the instruction to add, which would be this one. What I'm thinking of doing is, right now, these wires are carrying basically the outputs and the sums from the logic gates. I think if we just use some simple transistors, we can have a pretty easy configuration. So I'm going to get 3 transistors. And the idea here is the outputs themselves will drive the collectors. And then the signal from the instruction decoder will drive the base. So the power will only be able to flow to the LEDs when the base is activated by this LED right here. So I'm going to plug out power and I think give this a shot. I don't know if I have the space for this right now, but we'll figure that out. We have 3 resistors right here that are basically just limiting the current to the LED. And I'm thinking, at least for this example, if we just spread them out a bit more, then it might help us. So I'm going to just move this one to the side, keep this one in the middle, and move this one to the side. We want these 3 pins here to be the power for our collector. So I have a 2N3904 that we've used constantly. So the pins in order are the emitter, base, and collector. So I'm going to put the collector get its power from this output, this bit. And then I'm going to flip this transistor around and put the collector to this one. And then the middle one is really the only issue. But I guess if I move this over, then it can work. So these are all connected to the collectors, right? So we have emitter, base, collector, emitter, base, collector, and emitter, base, collector. So the resistors are all going into the collectors. And then now what we want is the LEDs to just basically go where the emitters are. Although now that I'm placing them, I think I have a bit of an issue. I think I'm going to get false positives, but let's see if it ends up being that way. So if we plug this in, then nothing should happen right now. Let's just double check that we're all disconnected here. So let's plug in power and we can see the add. There's a 1 and a 1 0. So the fact that the LEDs are not lit up shows that it's not operating right now. And that's because the base is not yet activated. And I'm seeing, of course, that I made a major mistake here. This base is always going to take the output of this button. They're kind of together. So I need to make some more space. Let me shift them all over. So I'm just going to spread these out some more. Let's give them some more space here. So let's add the transistors. And then on the collectors, the LED should go back. I feel like we might get some false positives. So the resistors are all going into the collectors of these transistors. You could see, of course, EBC, and they're all going into the collectors. And then from the emitters, they're going into the LEDs that are then grounded. So power's in right now. And again, we have a 1110 as the operands into this add, but no lights are showing up because the bases are not activated. So if we're able to activate the base just kind of by touching it with our, I guess, like human power, then we can see that they do turn on. The middle one should not turn on because there's a 0 coming from the chip, since it's a 101 outcome of 3 plus 2, so 101. So we can see when we touch them, only the first one and the third one turn on, which is how it should be. So what I want to do right now is wire it up with the output of our instruction decoder and see if that will work. So I'm going to remove the LED here, and then we're just going to get 3 more cables that go into those bases. So it's going to be a little messy, but let's see if it can work. This is all just temporary testing the concept. So I have a black cable and I need 2 others. Yellow and orange seem to work. There's yellow and orange. So what we're going to do now is basically connect the control signal, essentially, control line, we could say, from our decoder. So once the, I was going to say CPU, but that's way too generous to call this CPU. Once this circuit knows that we want to add, then he's going to alert the adder that he's got the go signal pretty much. And that's what we're trying to connect now. So I'm going to move this resistor over so that we have some nice slots available here. So I'm going to put them all in parallel with the output signal. I mean, really what I should probably do is just jump the connections between the bases and provide only one input. That probably makes more sense instead of all three of these cables. So I'll just use a black as the control line. Maybe that makes more sense. And then we need to connect them together then. So we need something that will stretch, let's see, 1, 2, 3, 4. Okay, it's a brown guy. So let's try and connect those bases together. And then the third one. All right, so those are now connected. It's very hard to see, but the brown cables are just connecting up the bases together. We just need to provide one signal to enable it. So I have my black cable here, which comes from our instruction decoder, and that goes into the base of one of them. And now let's see what happens. I'm pretty sure we're gonna get all three lights turned on, which is not correct. Yeah, so you can see that there is some logic happening here. So the middle light is a little dimmer. It's hard to tell on the camera, but he is dimmer, and it shows that he's not getting as much power, I think, because the collector is not powered right now. There's a 0 coming from the yellow cable. So all the power is coming from essentially the control line itself, which is still enough to illuminate it. So this solution does not work because we get this false positive. This is really telling us that the value is 7 when it really should be 5, should be 1, 0, 1. So I think what we'll have to do is use an AND gate for each of these, where the input or output itself from the sum and the carry, so basically the value itself, will be paired with the control line to create a clear 1 or 0, because this false positive definitely messes up the system. But there is a small win here. It does work as intended regarding the instruction. So if I activate the add, it only turns on when that instruction is being read into the decoder. If I put in the move one, which is the only other instruction that we have, you can see the add does not do anything, and then instead the move is turned on. So this is working well. We just need to kind of iron out the logic here to only output the correct values and not get false positives. So I don't know if I have enough space here to do the amount of AND gates that we need, although I think we may be able to. Perhaps if I put the LEDs first, then maybe that will be a better solution. Basically put it behind the input, but I'm not really sure. Okay, I think this worked. I think putting the LED first does seem to work, because we can see now he's the only one that kind of has this smart feature who will actually output the correct bit. And you can see that when I turn off this bit here, and now it's just 1 1, which makes 3, and 0 0. So we have a 3 signal, so it should be 1 1, and this should be off. This guy is on because he has problems, but this guy is on now, and he's off before when we put back in the 2-bit to make it 5. So 1 0 1, he's acting as he should. So I think this solution worked, where we just put the LEDs first before the transistors, and we ground it with the resistor. In this case, we no longer get false positives, because when the cable lights up the signals, then it goes into the bases of these transistors and goes out to emit. So it is not able to go through the LEDs. The LEDs are only illuminated when the current, if there is current, coming from the bit can be grounded. So this seems to have worked. I guess I'll set it up this way for the other two, and then that should be it. So I'm going to plug out my power and try to work on that. So I'm going to move this guy over even more just to make some more space. Although I don't think I need to do that anymore, do I? I think it's actually pretty neat now. So I'm going to put them back. I guess I'll leave the spacing how they are. And then all of the LEDs are going to jump over into the emitters. So this one's going to go from this guy into the collector of his transistor. And this guy is going to go over into the collector of his transistor. So we have our indicators back. And then we need to ground these transistors. And I think that's it. It's a pretty simple change. I thought it would be more complicated, but now an AND gate would be better functionality. But for now, I think this works. So let's plug in power and see what happens. Wow, that is real bright. I'm pretty sure I messed up something. Okay, there we go. So I think this works out really well. Now what we can do it's a 1 0 1, and if we take out this one, then when we enable the addition, we have a 1 1, so it should be 3, so it should be 0 1 1, and that is 0 1 1. If we take out this one, and we leave 1 0 plus 0 0, that's 2, so it should be 0 1 0, and that works. So this is working really well. The add circuit, which has its registers populated, if we want to call these registers, the bits are populated, only functions when the instruction decoder receives the instruction to add. When we do the move, then nothing happens. Only when we have the add 1 0 1 being processed in the decoder does the add actually fire off. So we're not constantly having the output being pushed now. It's only pushed when we need it. And I guess the idea would be that when the instruction decoder receives this instruction, it basically just pulses, and then the output is saved in some sort of register ideally. But this is a nice little start here, I think. So I want to put the buttons back in so we can really test it properly. And now it shouldn't matter how much we press the buttons until the instruction decoder receives the correct instruction. Okay, so we have our operands here right now, and it's 0 0. So if we activate the instruction to add by 1 0 1, nothing happens. But if we put in some values, so let's say 1 0, which is 2, plus 0 1, which is 1, we should get 3, we should get 0 1 1 as soon as the instruction comes in. So we can imagine that perhaps some instruction that happens first is like a move, right? So maybe we move the value to the registers. So let's say that we have some circuit that moves the values 2 and 1 to the registers. So we move, and let's pretend something happens. So 1 0 is saved and 0 1 is saved. So it's 2 and 1. And then let's say the next instruction that comes in is 1 0 1. So we tap that, and then you see the result there is 0 1 1. So this is really helpful. And you could see now, of course, that when we press 1 0 1, nothing happens because there's 0 and 0. So it is indeed adding, and the output is 0. But it only works when the instruction is in. So that's really cool, very interesting, and very useful, I think, for the future to have this wired up this way. Now, nothing particularly interesting happens right now. We're only displaying LEDs, but ideally this would be put onto some sort of connection that can be saved in other places. Usually it's like a bus. I guess we'll get there, but maybe what I should focus on next is adding a memory controller that we could hook up to this one, and then we'll be able to do some interesting things, maybe, I don't know. And if you didn't see the adder being built, it is filmed on a video, but I don't think it's that necessary. And the instruction decoder was built in the last video. And this adder technically has a half adder and a full adder. So it has a half adder for the first bit output, and then a full adder for the second bit and the carry. And essentially it takes a carry of the first bit if there is a carry, and then it uses that in its arithmetic. And then the instruction decoder, I was going to call it the destruction coder, but maybe that's another circuit that we should build. This guy was pretty simple. We're just taking a pattern and using it to dictate what patterns we want to drive certain circuits. So it's all been quite straightforward, I would say. I'm thinking I should still have some sort of output here to show when the circuit is live. Just something small, like a little add indicator. But yeah, really simple, and it's cool to see things adding together and sort of coming together into more interesting ideas. I've always been fascinated with this side of things, so it's cool to see it come to life. So we'll see what happens next.